So thank you very much for the introduction. As he said, my name is David Mallasén. I'm a PhD student at Complutense, University of Madrid. And today I wanted to talk to you about how we integrated Posit and Quire Arithmetic into the RISC-V ecosystem by means of the PERCIVAL Posit RISC-V core. If the clicker wants to work. So a brief overview of the presentation. I will start with a background on what is Posit Arithmetic. Then I will move on to the PERCIVAL Posit RISC-V core, some FPGA synthesis results in this case, some software benchmarks to see how this arithmetic does, and then I will conclude the presentation. So how do we represent real numbers on computers? Well, the most widespread way, I'm sorry, the clicker is not working. The most widespread way is using IEEE 754 floating point representation, which is composed of a sign bit and then a fixed number of exponent and fraction bits. However, in recent years, there have been some emerging alternatives. You may have heard of Google's bfloat16 or NVIDIA's TensorFloat, which are mainly focused on the AI domain. However, there are also some newer representations. For example, Posit Arithmetic, which is the one that we have used in our work. Well, Posit Arithmetic is composed of, sorry, I have a bunch of transitions, so I'm not sure if the clicker is going to work or not. Okay, now it seems that it's working. Okay, sorry about this. So Posit Arithmetic adds a new variable length field called regime, which acts as a long-range dynamic exponent. And thus, also the fraction will be of variable length. This allows for more flexibility in the trade-off between dynamic range and accuracy that a number can obtain. If we have a look at this graph, in the y-axis, we have the binary accuracy bit, so how accurate is a given number, and on the x-axis, we have the exponent of this given number. As you can see from the pyramid shape of how posits behave in this case, if the number is close to exponent 0, it gets some additional exponent bits. This accuracy bit, sorry. This means that it will be slightly more accurate than normal floats and doubles. However, if we move away from this area, floats and doubles still have a better behavior. That was for 32 bits, but if we go down to 16 bits, now the thing changes a little bit. Now posits will have 3 times as much dynamic range as floats, while still keeping this extra accuracy around exponent 0, around relatively small numbers. Posit Arithmetic also introduces the Quire accumulator register. This is a fixed point register. Just so you get an idea, for 32 bits, this is a 512-bit register, so it's quite large. But it allows to compute up to 2 to the power of 31 minus 1 fused multiply accumulations without any rounding or accuracy loss in the intermediate process. So the main point of this talk is the PERCIVAL Posit CPU. This is based on CVA6. We have been hearing about this already, which was Pulsarian, and is now maintained by the Open Hardware Group. This core supports a series of standard RISC-V extensions, and the ones that we were most interested in were the F and D extensions for single and double precision floating point numbers. What we did was adding to this core the XPosit RISC-V custom extension that we developed that added support for 32-bit and now also 64-bit posit instructions, as well as also this Quire accumulator register. Sorry. So just to have a better look at this extension, we add load and store operations for posits, also computational instructions, which is add, subtract, multiply, divide, square root, etc. Operations involving the Quire accumulator register, conversions to and from integer numbers, register move operations in the CPU, comparison of posits. So we have the full spectrum of instructions that you need to operate with floating point numbers. For this, we added support in the backend of the LLVM compiler for this custom extension that we developed, so we can write and compile C programs together with Posit instructions. Going back to PERCIVAL, we believe that this is a prime platform for comparisons between this new Posit arithmetic and standard IEEE floating point. Why do I say that it's a prime platform for comparisons? Because we introduced POSIT side by side with floating point. For this, we had to add a new POSIT arithmetic unit, as well as POSIT register file, and also load and store support. So if you want to have a look at the diagram of PERCIVAL, which is based on CV6, as I mentioned, in green, we can see the modules that we had to extend or modify inside the core, for example, the decoder to accept these new instructions, but also the register file, the load and store unit, the scoreboard, etc. And in the execution phase, we added in parallel to the floating point unit, or the ALU, our POSIT arithmetic unit that you can see there in orange. This POSIT arithmetic unit supports multi-cycle operations and has a similar latency to the FPU available in the core, which is FPNU. To input and output data, it uses a synchronous handshake interface. At the top of the diagram, you can see the computational units, but also we have the conversions to and from integer numbers. And at the bottom, you can see the operations that involve the Quire accumulator register. In this case, the multiply accumulate and the Quire rounding to POSIT. So for FPGA synthesis results, just so we get an idea, PERCIVAL runs on the Xilinx Kintex 7 FPGA on a Genesis 2 board, and the target frequency was 50 megahertz, which is set by the underlying core, the CV6 in this case. So for results, if we compare the POSIT arithmetic unit with 32 bits and 512-bit Quire with the FPNU, we saw that we needed around 3 times more resources than the FPU. This is a huge overhead, and we wanted to analyze a bit why this was happening. If we have a look at the individual cost of each unit, we saw that the Quire was taking around 50% of the area of the total POSIT arithmetic unit. However, this Quire accumulator register is not present or anything similar in IEEE standard. So if we subtract this cost to better compare both arithmetics, we saw that we needed around 33% more resources than floating point. This is still a significant overhead, but as we will see, there are huge benefits in terms of accuracy, and I will introduce this now. So for software benchmarks, we decided to look at the general matrix multiplication operation with 32-bit POSITs, but also now we pre-printed a couple of weeks ago a 64-bit version of PERCIVAL, and I wanted to introduce also one of the benchmarks that we saw there, which was the Cholesky matrix decomposition. So with these benchmarks, we are looking at 2 different metrics to compare these arithmetics. One is the performance, measured as FPGA runtime, and the other one is the accuracy. And for this, we looked at both the mean squared error and also the maximum absolute error that we got. So for the general matrix multiplication accuracy results, in this graph, you can see on the y-axis the mean squared error, so lower is better, and also note that it is in a logarithmic scale. So we saw that we got around 4 orders of magnitude lower error with POSITs with Quire with respect to 32-bit floats. And even if we didn't use this Quire accumulator register, we got between 2 and 3 orders of magnitude lower mean squared error in this benchmark. Now moving to 64-bit POSITs, comparing them now to double precision floating point, we saw that we got around 3 orders of magnitude lower mean squared error. This is the same graph as before, but for the Cholesky matrix decomposition as before. And now looking at the maximum absolute error, so how accurate are every output of the algorithm, we saw that we also got around 2 orders of magnitude lower error in every single value of the output. Moving on to performance, how well POSITs perform compared to floats, we saw that we were able to match the same performance as floats because the latency in the units inside the POW was similar to the ones in the floating point unit. And even if we didn't use the Quire and substitute these MAC operations with individual multiplication plus addition, we were also able to match this performance. And this also held for 64-bit numbers. So what's next? Well, I've been working right now in the Embedded Systems Lab at APFL, doing a PhD stay, and there we're looking to decouple this Posit arithmetic unit from inside the CV6 to have it as a standalone Posit coprocessor. So for that, we wanted to leverage the X-Heap platform and the extension interface from the Open Hardware group that was introduced a bit before. So just so you get an idea, we have the Posit arithmetic unit together with a small ALU for comparisons. We bundle it up together with a controller, a Posit register file, a decoder, and all of the things that we need to execute these new arithmetic standalone. And we made it compliant with the extension interface from the Open Hardware group. This means that we can plug our Posit coprocessor into any CPU that supports this coprocessor interface. On the software level, we are looking at some biomedical benchmarks that are running right now on 32-bit floats. And we saw that we were able to get less than 1% accuracy drop if we use 24-bit posits, and less than 4% accuracy drop if we halved the bandwidth, so with 16-bit posits. We also looked at the exact same thing, but with floating point 16, and the accuracy drop was over 15%. So here we can see that we could get a smaller area, better performance, and match or be close to the accuracy that FP32 can achieve. Also on the compiler side, we want to have a look and introduce built-ins and hopefully a native custom type into the LLVM compiler. This is a huge task. So if anyone out there knows a bit more about compilers than me, please get in touch. We would love to go in this direction as well. So just to conclude, we presented the PERCIVAL Posit RISC-V core, which is based on the CVA6, to which we added the XPosit RISC-V custom extension. FPGA synthesis results show that there's still room for improvement in this area and that we can still optimize the hardware for posits because it still has a bit of an overhead when comparing with standard floats. All of this is open hardware, and in the next slide you will have a QR that you can scan to access our GitHub repository. On the software side, we saw the XPosit RISC-V custom extension that we added into the backend of the LLVM compiler, and benchmarks results show that we could be as fast as floats while also obtaining around 4 orders of magnitude lower mean squared error and 2 orders of magnitude lower maximum absolute error. This provides an alternative solution depending on the application needs, and this is also fully open sourced. So as I promised, here you have a QR that you can scan to get into our GitHub repository. Everything is there. And I will be today with a poster as well, right next to the demo session. You can come and ask questions there. I will be glad to answer any that you may have.
Thanks a lot, 400 people are desperate for coffee. Now it's time for a coffee break. Thanks a lot for joining us. Remember, new posters in the poster session areas. Enjoy the break.